So, first module is introduction to hydraulic and pneumatic systems, and this is lecture 1, where we shall discuss what is hydraulic and pneumatic system. Hydraulics and pneumatics is more generally known as fluid power or fluid drive and control, but let us know what it is. Consider a load which is to be lifted to a height. There are many other mechanical means, but we can think of an actuator which is piston cylinder. We can put it vertically, and on the piston end we can put the load which can be lifted by means of lifting the piston through fluids. Now, we will think of supplying the oil to the cylinder, and we will think of a pump. So, we have put a pump. Now, we can directly connect this pump to the bottom of the actuator, and then we can lift the load. But the question is that when the pump will run, how we can take out the oil to lower the load. Therefore, we need some means that we have to take the oil out. Now, what we can introduce, this is a valve which is named as 4/3 directional control valve. I shall describe later what is meant by 4/3 direction control valve, but looking into this, what we find that pump is connected to one port, and then there are two ports at the top and another bottom ports which is apparently draining the oil. Now, we can connect this valve to the cylinder by conduit or pipe. Then one end is connected to the bottom, other end is connected to the top of the double acting actuator, and then if we looked into the left side of the direction control valve, then this pump will be connected to bottom, and there is a slight mistake in the arrow, then the top side will be connected to the drain and load will be lifted. Similarly, if we actuate this valve to right side, then this oil go to the drain and the oil will enter through the bottom, from the top, and load will come down. Now, we need a supply of oil to the pump, which is called reservoir, sometimes it is called tank also, and of course, as we are pumping the fluid, we need a filter there. Now, this pump will be driven by a motor or a prime mover, which may be electrical, which may be an IC engine, which may be other means of drive. So, this is the basic things and this would work, but there is another an important question, that if this load gets struck, then this pump which is pumping the oil will be pressurized, and there might have an accident because this hose can burst due to the pressure. So, if the pressure rises above some limit, then oil should go back to the reservoir, and for that we add an pressure relief valve. What is pressure relief valve? We can set a pressure here, limit pressure, which might be equal to the system pressure, slightly above the system pressure. So, if there is any problem, then the oil will pass through the relief valve and it will go to the tank, and thus the safety is maintained. Now, if we look into the industrial oil hydraulics and pneumatics, then why it is called like this? First of all, as shown in this diagram, fluid power systems use fluids to transmit power and motion, that we have seen. Both liquids and gases are called fluid. Hence, both these types of fluids are used in fluid power technology. Under liquids, mostly mineral oils with suitable additives, these are used instead of plain water, which however is used also in some cases, particularly nowadays again the water hydraulics is coming off. The main problem with water hydraulics is that it cannot be pressurized up to the level of the mineral oil. Also, there is a problem of rusting. Most of the components are made of ferrous materials. So, for water hydraulics we should go for some other material. Anyway, under gases usually atmospheric air is used after cleaning it suitably. However, synthetic fluids with additives and other gases are also used for specific purposes, such as fire resistance, or the fluid itself is the product, milk as an example. That is the state of art behind these two modern technologies of industrial oil hydraulics and pneumatics. Now, here I would like to mention, in hydraulics the fluid which is used is considered as incompressible, whereas in pneumatics, should it be air or gas, this is compressible. So, definitely behavior will be different, as well as we have to go for separate analysis for these fluids. Now, historical background is follows. Fluid power technology in its earliest forms mostly took advantage of the motion of fluids, or scientifically speaking of its kinetic energy. Water current to drive water wheels, example hydroelectric power generation as for an example. Wind energy was utilized in sailing boats. Those are based on hydrokinetic and also hydrodynamic principles. But oil hydraulics under the banner fluid power means the pressure energy of the fluid rather than its velocity is the drive force, or in other words we would say that we are using hydrostatic energy in case of fluid power. Therefore, fluid power with oil hydraulics, even called as hydrostatic transmission of power. In short form, we call it HST system. Oil hydraulic actuators, pumps and motors are termed as positive displacement units. Now, here I would like to explain. Let us consider an ordinary hydraulic pump, centrifugal pump. There we are using kinetic energy. When the impeller inside is rotating, then a suction head is generated through which the fluids come in, and that fluid is energized by the velocity, and then it is discharged at a pressure which may not be very high, but still we can supply the fluids with certain pressure. If we think of the turbine, there the fluids with potential energy converted into kinetic energy, and that transmit the power to the impeller of the turbine, and the turbine rotates. Whereas, in case of fluid power, we supply the pressurized oil inside the actuator, and it moves like when it is giving the thrust to the piston, it is like a solid bar generating a thrust on it. Alternatively, if we use the rotary elements, they are also the same pressurized oil is working, and that is why it is called hydrostatic. The question is there, do we use any hydrokinetic principle of fluids in case of fluid power? Answer is yes. When we are analyzing the valve flow, particularly flow in and flow out, we have to use also hydrokinetic part. But as far the power transmission is concerned, only we are using hydrostatic power. Pneumatics is also put under the same banner when pressurized air gas works at constant pressure, temperature and volume to transmit power. Now, if we look into history of development of fluid power, then we have to go back when Pascal invented his law in 1650 that pressure in a fluid at rest is transmitted equally in all directions. Then onwards, people started thinking of the fluid power system using this fluid energy. However, until the Bernoulli invented the law of conservation of energy in 1750, the fluid power did not crystallize. Now, first application of fluid power, or we should say the birth of fluid power, in 1800 when Brahma, an engineer, developed a hydraulic press using water hydraulics. His invention was not to use the power of fluid, but the leather cuff seal technology. He invented a water hydraulic press. Now, if we look into water hydraulics and oil hydraulics, Then with time it developed. Now, if I consider this line for the power transmission by water, okay, and in this direction we should consider this is the use of that fluid power. Then let us consider also oil hydraulics and pneumatics. Now, almost after 100 years, 1910, that the beginning of the last century, Constantinesco proposed an idea of alternating flow hydraulics. Now, what it is? You know alternating electric current and direct electric current, DC system and AC system. Now, in fluid power, if we have little knowledge, then whatever fluid may be with few pistons, we are pumping that are mixed, and then this is transmitted to the actuator. This means that this is not an alternating flow hydraulics, rather it is a direct flow hydraulics. Whereas Constantinesco he proposed the alternating hydraulics. However, that never popularized because of some engineering problem. Next, in 1920, Haleso Vacuum he developed high pressure vane pumps, as well as 1930 Thomas Doughty he developed synthetic rubber seals. He industrialized that seal technology. In fact, in fluid power, as it is a high pressure technology, the main problem was the leakage, apart from some other technical problems. So, when synthetic rubber seals were invented by Thomas Doughty, it actually revolutionized the fluid power systems. Not very far from that, 1940 to 1945 there was the Second World War. Then for meet the requirements of World War, many engineering developments took place, as well as the fluid powers also started growing rapidly. After that, in 1950, MIT, that is Massachusetts Institute of Technology laboratory, they in fact developed a fluid power laboratory just to give the theoretical supports to the fluid power components already being used or developed during the last few years. The outcome of that was published in a book, Fluid Power and Control, which was edited by Blackburn, Rayforth and Shearer, all are MIT people. Now, 1960 onwards, there is a rapid growth in advancement in components, fluid, air fluidics, oil fluidics, and many industries, academic research institute, they were also involved in research on fluid powers. Now, in between that, electrical engineering devices were also developed. So, it practically overshadowed the fluid power for the time beings, but it was found that fluid power is having its own applications. So, again the fluid power research and development started. Next, in 1980, the rapid growth in electronics, microprocessor, computer control, electronics control and drive that were introduced, and that was in fact was revolutionized again the fluid power. Now, if we look into the beginning of this century, rapid growth in electronics, manufacturing technology and nanotechnology has further developed this fluid power with the introduction of mechatronics, hybrid system, energy saving systems, proportional valves, again the water hydraulics, digital fluid power, virtual prototyping, micro hydraulic systems and nanofluidics. So, now we can say this subject is a combination of all engineering subjects. If we would like to know the fluid power control in better way, we have to know all these subjects. Now, we should look into what are the advantages and disadvantages of fluid power transmission over mechanical and electrical power transmission. Briefly, those are advantage that material, medium and heat dissipation. Heat can be dissipated easily through the body because the fluid is spreaded all over the cavity inside. Second, the second advantage is the inertia to torque ratio, as the fluid can be pressurized to a very high pressure and this pressure can be taken by the body because the body can be stressed highly. Therefore, inertia to torque ratio is very low in this case of fluid power. That means, very high torque can be transmitted at a low inertial force in comparison to electrical and mechanical devices. We shall discuss more in later. Secondly, that mechanically stiff, particularly oil hydraulics, the fluid, if we consider the bulk modulus, which is equivalent to the stiffness of metal, it is very high. Fourthly, high attainable speed response. The responses through the fluid is transmitted very fast. Fifth is the same medium can be used for both drive as well as control, but there are disadvantages too. Number 1, messy in general. Second, leakages control is a problem. Third, bursts of hose pipeline that causes accident, and we should take utmost care in this regard. Apart from that, in case of mineral oil, there is fire hazard and explosion may also occur. And fifth disadvantage, the contamination control is a problem, because some part of the fluid power is exposed to the air and it takes out the dirt inside, and cleaning this becomes a problem. There are many other disadvantages also as well as advantages, but those are minor. Now, again we will go back to the historical background. Now, growth in electrical technology overshadowed the use of fluid power, which I have already mentioned in the last decade of 19th century. This is 21st century. So, last decade of 19th century, that time electrical development was started, and then the fluid power was sitting back. Fluid power technology revived again in the mid 20th century because of certain inherent advantages. The high force to weight ratio of hydraulic devices makes its use very attractive, especially in situations where weight is at a premium, such as aircrafts and missiles. Now, sometimes it is called force to weight ratio, sometimes inertia to torque ratio. You see, if we consider inertia to torque ratio and force to weight ratio, this is just a reverse. In case of fluid power devices, force to weight ratio is high in comparison to the mechanical and electrical devices. Force to weight ratio in electrical machine is higher due to limitation of flux density in iron core. If we would like to generate a torque, we have to increase the torque, we have to increase the flux density in a iron core, but it is having own limitations. So, if we consider that flux density versus the weight, that can be comparable to force to weight in case of hydraulic machines. In comparison to that, very high pressure can effectively be used in much lighter body in fluid power machines, because fluid power ultimately generating stress in the body as the pressure is distributed all over the cavity. So, the body in which the fluid is being pressurized, that is also stressed in distributed manner, and the stress level can be kept within the limit for very high pressure. Now, basic elements in fluid power, already we have seen for transmission of power over a distance, usually 4 basic elements are necessary. First is the pump, which is invariably of the positive displacement type and whose function is to transform mechanical input power which drives it into hydraulic output power. The second element is the hydraulic motor or actuator, which converts the hydraulic energy back into useful mechanical energy at the point of application. The motion of this element may be reciprocating rectilinearly or over small arcs, or it can be continuous rotation, usually with directional reversibility. Now, reciprocating, you can easily understand that an actuator piston cylinder, and also as well rotary you can understand, say vane type or might be piston type, that can be converted into rotary motions fully, but there are also actuator which give some motion, not a full rotation, but it is reciprocating in a curvilinear path. In between the pump and motor, the fluid has to be conveyed through pipes or conduits of suitable strength and dimensions, and this is the third element. The fourth element is the controlling element, which is usually called the valve, and it may control pressure, flow and direction of the fluid and can be used by an operator or can work automatically under given conditions. Of course, a suitable reservoir for hydraulic fluid is also a necessity, as the fluid is recirculated in the system after repeated cleaning and cooling. Nevertheless, we need other components too for the finer control of drive or maybe for some other purpose. Now, in pneumatic system, it works in similar ways. When air is used as working fluid, it can be exhausted in the atmosphere without bothering for recirculation. This means that in case of pneumatic, if we filter the air to come in, then we need not bother about the recirculation because it is exhausted to the atmosphere. It has other advantages. However, the working pressure in pneumatic systems is usually 7 to 10 bar. It is much lower than hydraulic pressures, which 300 bar or more. Therefore, for pneumatics we need larger piston areas to develop a large force. So, if we think in this way, we will find that pneumatic under the fluid power banner, it has the separate applications than the hydraulics under the fluid power banner. Normally, hydraulics are used to transmit very high power and pneumatics are used for the small actuation and control. Now, valves and fluidics. The control of fluid power system is done usually by the valve, which we have mentioned earlier. However, a modern method has emerged since about 1958, where the controlling action is performed by one fluid jet acting on another fluid stream or jet. The pure fluid devices are called fluidic or fluidic devices. The word fluidic being a combined word out of the two words fluid and logic. This means that the fluidic devices also can be used as a valve. However, initially the fluidic devices was only pneumatic. Therefore, it was being used for mostly signaling, not the valve where we need the larger force. However, where the pneumatic was used, there we could use the fluidic devices also as a valve. This technology is more suitable for pneumatic application, which I have mentioned, and that also under low pressure. For high pressure valves with moving elements are most suitable. Now, we continue this with basically valves and fluidic devices may also be called as switches, and as one of the main functions of a switch is to put on and off power, it can be used as a two state device with outputs on or off. Or in terms of binary system 1 or 0, or in terms of symbolic logic true or false. This makes it possible to use the switching circuit algebra, also known as logic circuit algebra and Boolean algebra. We will learn this topic separately in a different lecture later in this course. Application: design of telephone exchange and computer switching circuits, where we used these logics. Also in fluid power technology as well, without at all bothering to interface with electrical elements. Now, control of fluid power. We know that power is equal to force into velocity. Now, the force can be resolved into pressure into area and then velocity. Then we can write pressure into flow rate, which is the output of a pump. But we should remember, the pump output is the flow rate, not the pressure. Pressure is experienced by the load we are transmitting or the motor torque to transmit the load. Hence, fluid power control involves control of pressure and flow rate. By using a variable restrictor in the passage of the fluid flow, fluid flow rate can easily be controlled. Now, this is a valve which is shown. This is very schematic view, but what I find, the flow is going in and there is something like screw which is restricting this path. Now, this, by doing so, what we can do, we can control the flow as well as pressure. Now, pressure control is done for keeping it below a safe pressure, and arrangement is shown in the following illustration. Now, in this case, what is there? The flow, if you look into this figure, flow is going in from the bottom, and then as if there is a body which is called poppet, it is under a pressure of a spring. The length of this spring again can be controlled by a screw. So, what happens when there is a certain pressure, only then this opens and fluid can go out, otherwise normally this flow is going to a system. So, this is the basic concept of pressure relief valve. The poppet valve is kept under variable spring pressure, which I have described, to put a stop to the flow. When the pressure exceeds the spring pressure, the poppet gets lifted and the pressure is relieved, or we can say it is controlled. Most simplest but essential of this category is pressure relief valve. In fact, the pressure relief valve to be used in all fluid power system for the purpose of safety. A simple fluid power system application example is that a spool type valve is often used for controlling flow and direction. An example of simple fluid power application is shown in the following illustration. What is there? We find a load is being lifted and there is a valve. This valve is a simple push button type. Now, fluid supply is here. Now, if we push down, then this fluid will go to the system. Now, if we again remove the pressure on the push button, then this fluid will go out. Which I have already described. The push button allows the working fluid to enter the actuator cylinder as to exhaust out of it. Pushing the button down makes the load rise up, and left alone by itself, the valve spring pushes off the valve and the fluid comes out of the working cylinder to exhaust, bringing the load down. The valve is controlling here the movement of the load, but an accurate movement of the load through definite distance is not ensured here automatically. However, it can be achieved by knowing the system characteristics and or an accurate calibration curve, and of course, with specific valve geometry. This means that we can control this valve to get an say desired rate of flow, etc., by controlling the orifice. Such type of controlling is known as open loop control. Now, what is closed loop control in fluid power? Referring to the earlier system, if however, the movement of the load was made to act upon the controlling valve to get a desired output, it would be a closed loop control. In order to let the output be monitored continuously with the input, a feedback loop is needed. The concept is represented in the block diagram as follows. Now, what is there? An input, then error detection, then actuator, process or plant, then controlled output, and there itself a feedback which is coming to the error detection, and then it is on controlling the actuator. Now, we can think of the servo mechanism, which is also with hydraulic. The servo term as you know, it is feedback control of motion and position. So, a schematic view is shown here. This is the load, it is being moved with an actuator and there is a valve. Now, the system is like that. When we give an input, then the load moves, but looking into position and motion, the valve body, outside body also moves, and by that closing the motion of the load, and again with the presence of input, the spool will move further and load will be moved. Now, if there is an feedback control within this system, then we shall call it servo mechanism, and there is a wide application of hydraulic servo mechanism starting from the machine tools to many other, say even if it is in the missile control. Now, here this is further explained as like that: an input effort x, say from the left to right, will produce a large force output to move the load through a distance y proportional to x. In a copy lathe, for example, the input x would be generated by a template follower and the output y would be the cutting tool position for reproducing the template shape. Here the valve is doing the output measurement and error detection, and also it is supplying the corrective power to the working cylinder. Now, automation system using fluid power, it is a schematic view is presented here. In many systems, the control arrangement required may not be aimed to do only a particular simple operations, but to control sequences of operation. Such sequence controls may be event based or time based. That means, looking into the event, this control is being operated, or maybe on time. When a particular action takes place only when the previous event has been completed, it is an event based sequence. But when a number of events are ordered to be completed according to a definite programmed time interval, irrespective of the completion of other events, it is a time based sequence. An example of an event based sequence operated by fluid control is illustrated next. Now, look at this. The system is used for lifting an object from one conveyor level to another automatically without any human intervention. The sequence of operation consists of first extension of cylinder A rod and then B, and then A and B retract and wait for the next object to come. Say it is like that, an object is coming in, then with this cylinder this is lifted to this conveyor. What is there when this load is coming in, then this object sensor is there, which is sensing the object is on this A cylinder. Then this will be lifted and there is another lift sensors which will give an indication to the cylinder B, and that will be pushed to this conveyor, and when this push will be completed, it will push another sensor which will go back to the again initial state. That means another object will come. So, this is a simplified schematic view, but actual will be very complicated, and designing these are all maybe with fluid power. These actuators are using the fluid power, sometimes these are with the fluid power or with electronics. Now, this lecture is prepared with following these books, and these are mostly books. One is the Control of Fluid Power, authored by McCloy and Martin. This is a very good book. Now, Electrohydraulic Servo Mechanism by Morse, also an important book. Similarly, Design of Hydraulic Control Systems. Hydrostatic Transmission System by Korn. This is available in our library. And lastly, I have followed also Fluid Power and Control by Blackburn, Rayforth and Scherer, which I have mentioned earlier. Now, organization of this lecture series. So, this was the introductory lecture. So, first lecture. Now, module 1 will be introduction to hydraulic and pneumatic systems. There are few modules, I will describe one after another, and each module is having minimum 2 to 4 5 lectures. Now, our next module will be the fundamentals of fluid flow and fluid properties. Next one, module 3, hydraulic valves and other components. Module 4, electrohydraulic valves. Module 5, introduction to hydrostatic units. pumps and motors. Module 6, hydrostatic transmission systems. Module 7, fluidics and fluid logics. Module 8, special topics on hydraulic systems design. Module 9, pneumatic system components. Module 10, non-linearities in fluid drive and control systems. And last is appendix. This is actually miscellaneous things. Maybe sometimes some problems are solved there, as well as in many lectures you have to follow the appendices for the further study of that portions. However, we shall go one after another, but sometimes it might be that we can jump to other module instead of continuously following the sequences. And that is all. Thank you very much for listening.